Okay, so it's recording. Okay, so it's recording now. I already have this. So let's do conda environment list. Conda activate. I-37 ITS 520. And this is going to be section, you guys are section 2. Now, keep in mind, a lot of this code may be very familiar to you because really, you already know how to do deep learning models, right, in PyTorch. The only thing is now we're going to do architectures for classification. So there's going to be a few little tweaks here and there. And the fact that we're dealing with images or something, but otherwise, a lot of the code, that's the beauty of this, right? So you're building that skill where a lot of things should be familiar to you. Okay, so we are going to, so our data will be CIFAR10, basically. Maybe I'll create a new folder. There, I'm going to call this classification, which is the new module for the semester. Okay. And then we're going to cd into that. Now, a lot of classes in machine learning will usually start with classification. I just kind of like to start with regression because I think it's much more intuitive to understand before you start dealing with images. All right, so we are here, so we can go ahead and start our Jupyter notebook. Okay. Right. Okay, so let's move this down. All right, so I'm just going to call this one, I'm going to rename it, and I'm going to call it CIFAR10. So I think I've mentioned this before. This is probably classification. Okay. So in classification, now we don't, now I want you to understand that for classification, it's not just images that we're processing. You know, iris was not images and we were doing classification, but it's just traditionally classification uses a lot of image data. All right, so basically we've so far used iris and we will use 2 more data sets, CIFAR10 and MNIST. MNIST actually came before CIFAR10, but it was only black and white. CIFAR10 is actually color images, which I think we've seen already. So I'll describe those a little bit. So we'll do these 2 data sets, and probably there might be a 3rd data set that I still need to figure out which one I want to assign. And as I said, it'll be another competition style approach. And that'll be homework, of course. So there will be probably 2 homeworks in this topic in the next 4 weeks or so, right? Just remember, we have our second exam week 12, right? And so there will be that as well. And then we'll wrap up with the generative models. We are on a good question. This is week 9. Yeah, so we'll have the exam 2 on week 12. Yeah. Yeah, so that somewhere there, we'll do the exam. And then, as I said, your homework assignment. All right, so let's see where we go today on this one. And then I won't assign both MNIST and CIFAR10 for you to do object-oriented, and really shouldn't be that much work, I don't think, but we'll see. All right, so let's start today with CIFAR10. So let's just call this CIFAR10. This is a data set. Okay. And let's provide some details. So basically, it's got a lot of data. I mean, this is not considered big data by any means. but it's a big data set compared to obviously Iris, which only had 150 samples. Okay, so it's used for classification. So it's used for classification. And we have in this 10 classes basically. And the images are like of cars, airplanes, birds, etc. We're not going to use all 10 classes for this one. We're just going to select a few classes, or maybe just 2. Okay. So it's got 10 classes. It should have about, so CIFAR10 consists of about 60,000 or so training images. Or images in total, I think it's 60,000, of which 10,000 are for training. Or sorry, 50,000 should be for training. We'll corroborate this, but I believe these are the numbers. And 10,000 are for testing. Got it? All right. Another important feature that's very useful about CIFAR10, as I said, is that whereas MNIST is in black and white and makes things easier, CIFAR10 is in color. So that means it is RGB. So we have the 3 channels, okay? And also the images are small, which is nice, so that we don't have to require big computers. The images are about 32 by 32, okay? So, which I don't know what the number is, but it would be nice to have it computed. All right. The classes are labeled basically 1 to 10. Okay. So for instance, you know, I think airplane is class 0, right? And then car is class 1, etc. Okay. So that's basically the approach. So I'll add this in. That is CIFAR10. Okay. We're going to add a few of our libraries that we need. I'll add them as we need them. I'll add a few right now. Obviously, we're writing in Torch. So I'm going to do import Torch. And then import NumPy as NP. Import OS. We will, you know, a lot of the difficulty with these kinds of things is dealing with the images. Okay, so I could give you a data set that has got physical images, you know, or I could give you a data set that is maybe an Excel spreadsheet. I don't know yet for the competition. I'll see. But that's dealing with that data can be challenging. Okay, so that's usually a hard part. So just be aware of it. Okay. So a couple of things we're going to use for this is Torch Vision. So I'm going to do from Torch Vision import datasets. So CIFAR10 should be available already. Now, when you deal with images, you have a lot of things that go into processing an image. We've talked about things like normalizing images, converting images into tensors. But really, there's a lot of things that you can do to an image. In fact, you could take an entire course called image processing, just about techniques for processing images, okay? So what has happened over the years is that tools like Torch Vision have been created, which have all of these things built in, okay, for dealing with images. So obviously, this is not an image course. I'm not going to cover a lot of these, but at least we'll print out some of them and I'll list them for you to have available. And we'll use a couple of them. So these are usually called transformations that you perform on your images. The module is called transforms. So you're going to do from Torch Vision import transforms. Okay. So let's go ahead and hit run here. We're going to use sklearn to evaluate performance. And this is one of the lectures I want to do, maybe at the end of class today, if time permits. Just we'll start looking at the performance metrics. Remember, whereas in regression, we use the R squared, here we have a set of different metrics all derived from the confusion matrix that we saw last week in WECA. And this is going to be the thing that we will use for the computation, basically. All right, so we'll come back to some of these. These ran. So let's go. That should be enough for us to get started. I'm going to go ahead and in here, I'm currently in the folder in this folder, right? So I want to create a separate data folder in here. So let me just go to the desktop. And I believe it's down here, one of these. Should be, you guys are section 2, so I'm going to go in here. And in classification, I just want to create the data folder here. So I'm creating a new one called data. And because, this is where CIFAR10 will download its data, and these can be big data sets. Okay, so let's go back over here. So I've got my data set there. Now I'm going to proceed, right? So I'm going to create data path, and then I'm going to say data, and then CIFAR10 data. Any questions, guys? So we've done this before, I think, really quickly in a previous class, but now we're going to use the data set. All right, so we are just downloading it from data sets, but keep in mind, as I said before, in the homework that I give you, I may give you the actual images. And that's that's all I'm trying to stress is that's an important problem to solve. Okay, how do we read from images and load them into tensors? Okay, that can be, it's not a trivial. All right, so let's go ahead. So from data sets, obviously this makes it easy for me just to import the data and load it into a variable called CIFAR10. It will also download it to a folder on my computer, so I don't have to read it in every time from the internet. So CIFAR10, let's say this is going to be the training set. So I'm going to say training here. And then I'm going to do from data sets, CIFAR10 data path. I'm going to do train equal true. And I'm going to do download equal true. Okay. All right. So let's go ahead and hopefully this will work for you guys. So let's, and for me as well. Okay. So it's downloading. It's downloading big things, right? Welcome to the world of big data now. All right. So, although this is not big data, as we start going deeper into deep learning, we start to have resource issues, things that take a long time to process. In the 530 class, this is actually one big challenge that we have is, because we have the models require big things. So, it changes the dynamics a little bit. Okay, so we're going to give it a minute to download. Well, while it's doing that, I guess we can continue to write some of the code. Let's do the same, but for the test set. So I'm going to say CIFAR10 test, the test set, right? And I'm going to invoke datasets dot CIFAR10 data path train. We're going to say false here instead of true. So it's not the train set. And then we can say download as well equal true. Okay, so that one finished. Now we can run this one as well. And that way we should have our train and our test set, basically. Questions? Oh, it finished already. Great, because I think it's only 10,000. So now we have our data. And basically, what would be the approach here? The approach will be, we have data. We're going to try to load it into the data loaders as we did before, because we want to take advantage of those data loaders that PyTorch provides. And then we create the architecture, right? And this is going to be an architecture for classification. So there's a few tweaks here and there. Different loss function. Okay, but we don't have to get into the equations of it because we can just use the built-in loss functions in Torch and then train and test. And a lot of that is pretty much things that should be very familiar to you because you, in the competition, I'm sure you ran this many times, right? And so that's great. All right, so now that I have this one, let's print out some details of the data set. I'm going to do print. And I'm going to print CIFAR10 training. All right, so I'm going to hit save. All right, so CIFAR10, as we can see, it has 50,000 data points. And this is the train split, as we can see over there. So basically, 50,000 images. That we're going to classify. The labels should be there as well. So let's say that you want to, well, let's actually do the test set as well. So I'm going to do print. Print CIFAR10 test. I'm going to hit run. And as you can see, this one has 10,000 images or 10,000 data points. And this is labeled as the test set, basically. Okay. If we want to view one of the images for either one, we can try to do that. Go over here and we're going to say IMG train, just some example with its label. And that's going to be CIFAR10 training. And then from here, we're going to use square brackets. And you can pick a value, let's say 42. All right, so I'm going to hit run. Okay. And now let's print out the label. And as you can see, this one is label 2. Okay, so what does label 2 mean? Well, we can actually view it, hopefully, by doing IMG train. And hitting run. And that is, what is that? A wild turkey? An ostrich? Okay, great. All right, so as you can see, that's what's in there, right? So probably the classification, ostrich for that would be too specific. It's probably a bird, right? So that might be the actual classification. But, you know, I don't know. We can do the same for the test set. So take a similar approach. I'll just copy this one. So I'm going to do IMG test label CIFAR10 test. There's 10,000 in there. So there should be an index 2, 3, 4, 5. Hit run. Okay. Let's do the same thing. Label is 1. And IMG test is a, what is that? Oh, it's a car. It's a car. Okay. And so that's basically, as you guys can see, their color images, they've got their labels. Make sense? Okay. So what we need to do now is basically go from this to tensors to data loader. That's kind of the pipeline, right? That we want to follow as far as the process. But we got to take several steps in here. All right. So one thing that we're going to look at is we've got from Torch Vision this thing called transforms, right? And as I was saying, this is something that allows us to process our images efficiently. Okay. You don't have to do this from scratch. You can just use functions. So it's a little bit to get used to it first, but the power of it is that once you know how to use it, you have all these different transforms that you can easily apply, hopefully. So let's go ahead and do print dir for directory, and then let's do transforms. Okay, transforms. And this should give us a list, I believe. There we go. So as you can see, the list, too much. It's a way of processing our images. So what does it say there? It says augmentation mixed, auto augment. So that those, when you see the word augment, it's literally like it's adding something to the images. Okay. Center crop, I think that name is self-explanatory, right? Color jitter, you know, you basically process the image, compose, convert image to a data type. 5 crop, Gaussian blur, grayscale, also self-explanatory. Lambda, linear transformation, normalize, that one, you guys should have a sense of what that is, right? What is normalize? To change, yes, go ahead, please. Yeah, exactly, right? So these images have values that are 0 to 255, right? On each of the channels, and we would want to convert them to a normalize of 0 to 1, for instance. Why do we do that? Machine learning seems to work better with that. Now, we didn't see that in the regression challenge, right? We didn't see that effect, but hopefully now, as the problems get more complex, the neural networks get deeper and more complex, normalization becomes crucial for the models to learn. Make sense? But as you can see, it's the same ideas as before. All right, so it's got random augmentation, random just adjust sharpness, random apply, random auto contrast, random crop. Why a random crop? Seems like a strange thing, right? The crop an image random. Why do you think there's something called random crop? It's basically to make your images, to augment the images, to make them more diverse. So like, for instance, you know, let's take this, for example, right? This is an image of a car, but a random crop might just crop like this part here and crop out the rest. And that becomes an image of a car. And then it does this part over here and it crops out the rest. And that becomes an image of a car. If you notice, it's the same car, but it's like there were 3 pictures taken instead of 1. They're all of a car, just a partial car. So the idea is that something like a CNN, for instance, should be able to start to see the pattern in all of these, right? And so you can do that in these types of problems. Random cropping, augmentation, etc. You know, if you have an image of a pepper, right, you can stretch it, for instance, or put noise in it. This is equivalent. Flip it, you know, that kind of thing. It's still a pepper, right? Just in a different view of it, like somebody looking at it in a different perspective. Got it? All right, good. So yeah, so these are, I won't show examples of each of these. I mean, I leave it to you guys to play with. I'll show examples of just a couple of these. Again, you will have a challenge. Use every tool at your disposal to win it, okay? So we have a few other ones. Random size crop, random rotation, that's the same idea. Random vertical flip, it'll flip it for you. Resize, obviously. 2tensor is one that obviously we will need to use because we need to convert the images to Torch tensors. So I'll show you how to use that one, and so on. Okay. There's more. There's a lot. Any questions, guys? Torch vision is extremely powerful. Okay, it's extremely powerful. All right, so we printed the images. So now let's take a look at this idea of the transforms in a little bit more detail. So IMG is basically currently an object, right? So let's see what kind of an object it is. So I'm going to take image train, basically. I'm going to take image train. I'm going to take image train. I do print image train, and I'm going to hit run. So as you can see, just from this information, what is image train? It's a pill image, right? Pill is a standard image format for Python. Tells you the size, 32 by 32, tells you it's RGB. It's an image, okay? But it's not ready to fit into neural networks in PyTorch because we need to convert it into a tensor, right? A torch tensor. All right, so let's see how we could do something like that. So you saw that transforms contains all of these. So then we can reference those functions through transforms. So I'm going to do transforms dot to tensor. Okay. And as you can see, this is how I'm able to access this one over here. Got it? This image is probably right now 32 by 32 by 3, right? Why 3? Because it's RGB, right? It's got the 32 by 32 3 times, right? So keep that in mind, because how do you deal with that? You see that throws in a problem now. So what's one suggestion? We can spaghettify it, right? So what does that mean? It means that now we would have 32 by 32 times 3, whatever that number is, which is probably pretty large. So think about that. We've gone from very tiny things to large things, okay? And that will be another challenge for your work. Let's say in the competition, if you start building architectures that are bigger, many layers, you may run out of memory, fortunately, right? So what would you need to do in that case? I think some of you had asked me about this. So GPUs, right? That's where the GPUs come in. But I don't know if you guys have GPUs on your machines. You might, but that's a challenge, right? So it's a trade-off. This is why in a competition, if Google's there or Facebook, I mean, they have unlimited resources, right? And so unfortunately, this is one downside of AI. The current state of AI is that we require, sometimes you need too much computing power. But anyway, let's push this to the limit. It may be, I've had this happen in a class before where the student that won was simply the student that had the GPU, because they were able to run 100 scenarios on their GPU much faster. Lenny, go ahead, please.
I got a question.
Yes.
But let's say someone has some code or something that they think and they prove if they had enough resources could become the next more efficient model. You can Google or Facebook, but then lend them the resources for.
Wait. So if you had a new algorithm, you mean?
For someone, yeah.
A new CNN that where every CNN gets 75% on that problem, yours gets 85, right? And then what's the question?
If you're saying the problem is people don't have enough resources, people come up with new ideas and concepts, Google and Facebook.
Okay. I see where your question's coming. Jason is working on this problem actually. Right, Jason?
I mean, I guess one thing that I found on AWS is that I think I mentioned this to you, but they have something where students can get like a $5,000 whatever free amount of usage on their platform. Yeah, and then professors can get even a higher amount to do what might possibly be experimentation that could provide new results.
Yeah, but to answer your question, I mean, it's a proof of concept thing. If you think you've got a good, promising algorithm, try it with the resources that you have, and then as you need to scale up, I mean, if it seems worth it, you know, you'll pursue any avenue. And those companies, as you say, I mean, yes, if you had something novel, they'll look at it. But really, there's other. My point is something like GPT models and Chat GPT. Not everyone can train them anymore, right? It's becoming limited. Only because even though the data is available, it takes 10,000 GPUs or something to train one of those models for 3 months. That's a lot of money. That's in the millions. You see what I'm saying? So this is where we're unfortunately at. And it's starting to limit what creative people can do, right? And so we need to explore other approaches, like what Jason is actually doing. But to answer your question, I mean, you can rent, certainly, you can rent GPUs. We do have some GPUs here at the university and something called Scholar and Gilbreth that we can sort of borrow, but it's a queuing system. So what that means is you have to kind of like request to use it, and if there's a GPU, it'll become available immediately, or it can take an hour for you to have access to it. But I'll look into that to see if we can get it again, and just keep in mind you'll probably have to use it at 3 a.m. on a Saturday because you know it's the whole Purdue system that is queuing for this.
We
Yeah.
experienced that in Professor King's class.
Yeah, we did.
Oh, you've already tried it, yeah.
Yeah, probably not for the same thing, but we did have to use it, and there were times where I would just be kicked off.
Yeah, it's a queuing system, so unfortunately, you know, if we're at a peak time like right now or at 4 p.m., you'll never get access to it because everyone, even classes, are trying to get into it. But for research, if you feel like Lenny is, that you have a good thing and you just need a GPU, if you're willing to do it on a Saturday or Sunday at 3 a.m., you know, that might work for you. Okay. Otherwise, AWS could have some free resources. Okay. Yeah. All right. But anyway, to go back to what I was saying, this has happened to me before, and it's unfair, but it's the current state of AI. The student that won a competition last year was just the one that had the GPU, and they were able to run tons of scenarios really quickly. Okay. Got it? All right, great. So let's keep going. So we're invoking the transforms from transforms to tensor. Okay, and so what we can do here is that we define like our own function to tensor like this. All right, and then you'll see why this is useful in a sec. But although you could use this one directly if you wanted to, it's just a different way of writing it. And now what we would do is we would take that same IMG train, right? So this one here, and we're gonna do to tensor like that. All right, so to tensor IMG train, and this will return hopefully our image train, and then TR, right? Which just indicates that this image is now a torch tensor. Questions? So let's go ahead, and how do we test for this? We can go in and just print this out, as we have seen many times before in the semester. So this is going to be IMG TR dot shape, right? Well, what do you expect the shape of this to be? Oh, IMG, it should be IMG train, right? What do you expect this to look like with dimensions? Yeah, so what would be the values? Yep. Notice that it already did what PyTorch requires, which is basically that the channels should appear first. Remember that? We talked about it. So keep this in mind because the other functions are built kind of assuming that you already achieved this. Okay. So if when you're doing your homeworks, etc., make sure that convert it to this format so that all the other functions work on it. Okay. All right. So now that we have done that, we can actually show how we can use a transform on a data set itself. So we can do, for instance, here, let's call CIFAR10 train or training. Let's now call it tensor. Oops, sorry. Let's call it tensor CIFAR10 training. And then we're gonna call the data set. So data sets dot CIFAR10 data path. Oops, sorry. Should be lowercase. Data path, comma. We want the train set again. True. Huh. Should be highlighting. Okay. Now notice here, I'm going to do download equal false. And the idea is that it should retrieve it from the folder that we already provided. Okay. We'll create it. And then this is the trick. It's got a parameter called transform. And this transform parameter allows you to assign to it transformations from this list. So basically, it'll just do it for all the images. Got it? Does that make sense, guys? So you don't have to do it, it just does it for you. And this then gives you the entire data set already as a torch tensor. So it should save you some work. Okay. So we can invoke either toTensor or just transforms toTensor. So I'm going to do transforms dot toTensor, just like that. All right. So let's try it. Let's run it. Yeah, please.
It said it's a raw cell, not a.
Oh, is that why it's not highlighting? I must have clicked that incorrect. Okay, thank you. Yeah. All right, there it is. There's the highlight. All right, so hit run. Okay, so it should be reading from the folder, not from online, and it should have converted them to tensors now, right? So how can we test for that one? Well, we can read in one image. So I'm going to read from tensor CIFAR10. And let's pick one. This is the train set. So there should be like a really big, so 23,456. And we're going to assign this to IMG, comma, label again. But this time, it's not an image. It is actually a torch tensor. So we can do something like this to remind ourselves it's already in the correct format. Remember that it needs to be in torch to be able to be loaded into the torch computational graph, right? And in order for it to run. Okay. So then, let's go ahead and run this one. Oh, error. Oh, yeah, training. You're right. Sorry. Thank you. Okay, let's run it again. There we go. Okay, so it worked. And now we can print the tensor. So we're going to print the tensor. And that's going to be IMG TR. Okay, so if we run this one, we should be very familiar now from the basics part of the semester where we played with tensors, etc. This is a torch tensor. Any questions, guys? All right. Now let's go ahead and how are we gonna do that? Okay, so we're gonna think about normalization of the images. Okay. So let's go over here. Normalize. Okay, so I'm gonna convert this to a data cell. Markdown. Hit run. Okay, so how do we think about this? So normalization was usually what? Taking all the values in all the images and averaging, right? And finding the average. Do you remember that? So we can do this on a cell-wise basis, or we could just take the average of all the values in R, the average of all the values in blue, the average of all the values in green, right? So we can do that. So let's try to do that. This is just an example. So let's do images list. Okay, we're going to create a list here. IMG T for tensor. And then we're going to do a list comprehension. So for IMG T, comma, we could say label or just discard it by using a underscore. Okay, so I'll just choose to do label here. We're just not going to use it. So for that in tensor CIFAR10. CIFAR10 training, right? Okay, so if we look over here, we have this data set is what we're looking at. So let's run that one. Okay, it's running. It's iterating through all the images. So this process will take a while because it's a for loop. Taking a while.
I think it's done.
It's done, really?
No, it's still dark.
No. I didn't.
Yeah, my computer's just, I don't know, there's something going on with this computer.
This was fast downloading the data set though.
Oh, really? Yeah, I don't know. Honestly. Okay, now it's done. Like, if you can tell me how to make this thing faster, right? I would be very happy because it's new. It's not even new. All right, so let's take a look at images list. Images list, right? So there should be a lot of images in here. You can see the images in there. They're basically torch tensors. If I do len, it's a list. It's 50,000 images. So it's 50,000 torch tensors, and we established that torch tensors are 3 by 32 by 32. Do you see that? This is where deep learning starts to get complicated, okay? Because we're dealing with dimensions, and we have to think in terms of multiplications of these matrices, okay? So let's create this, let's make this list into one single tensor, okay? Let's try to do that. So how do I do that? I'm going to create IMGs. Let's call it all IMGs TR. And we're going to use torch.stack, which I think you guys use something like this in one of your homework assignments for. And what are we going to stack? We're going to stack the contents of IMG's list. Okay, so all the tensors in this list, we're going to stack to create one single torch tensor. There are 50,000 of them. And the question is, how do we stack them? What do you guys think? So the images are 3 by 32 by 32, right? Yes? Is that what the images are? And then we're gonna put them on top of each other. And now the tensor will have, there's 50,000 images in it, right? So let's just see. Probably the best thing to do is just play with the parameter called dimension. Okay, so there's at least 0, 1, 2, and 3, right? Possibly. So let's do 3 first, and then we're going to work our way down and just kind of get a feel for what's happening. We will also print the shape of this just to see what happens. IMG's list, oh sorry, all IMG's TR, right? It's going to be all IMG's TR. As I said, I cannot stress enough how this is what becomes difficult when you start going up the deep learning models. Okay, it becomes very hard. So trying to keep things in a standard way is a good idea. All right, so let's do shape here. And let's hit run. All right, we created now one single torch tensor, which is 3 by 32 by 32 by 5,000. Do you guys see that? So basically, we're putting in our images on top of each other, and there's 50,000. Oh. Got it? Just for the curiosity, let's do 2. See how it stacks them now? So it did 3 by 32 by 50,000, sorry, by 32. But this might create problems in the way that we would process the network. You see that? So you kind of always want to find the right approach and keep that in mind. Let's do 1. So you might expect the behavior of it to be such as this. 3 by 50,000 by 32 by 32. And then let's do dimension 0. And it'll be 50,000, right? 50,000, 3 by 32 by 32, which I would actually be inclined to think this is actually how we should go about it. But the problem is Torch wants things to be in a specific format of 3 by 32 by 32. Does that make sense? So these are the things we kind of want to have to get used to. Remember, we're also going to do things in batches. So if our batch is 64, then here it would be 64 by 3 by 32 by 32. Got it? So anyway, that's just an example. So let's take a look. Let's set it back to 3. Leave it like that. All right. So now that, okay, so we've got 3 by 32 by 32 by 50,000. So basically then, let's see what we can do. Now there's this thing called views or view in Torch, which allows you to kind of like resize, reshape things in a tensor, right? So let's see how that works. So let's do view 1. Oops. View 1. And that's going to be equal to all IMGs TR. Because remember, we're dealing now, we don't want to have the list, right? Instead, we just want to play with the entire tensor altogether, which has all the data. So we're gonna do view one equal to all IMGs TR dot, and now Torch has this function, view. Okay, and this allows you to change the shape of something. Okay, so for instance, let's say that we did 3, comma, -1, comma, 50,000. Just an example, right? Now here, yeah, and then we want to print the shape of this tensor. Oops, sorry. So we're gonna do print view one dot shape. What do you think? What did we do here? We decided that we wanted that tensor to stay with the first value being 3. Remember, that's the RGB. We want the last value to be 50,000, but we spaghettified the 32 by 32 from a 2-dimensional into a 1 vector, right? Does that make sense? Multiply 32 by 32, I think it should be 1024, right? You can corroborate. Do you see how that works, guys? So that minus, I think we've also played with this in NumPy a little bit at the beginning of the semester. And this is where you start to use these things now for the architectures. Any questions? Lenny, yes.
So what happened, like, let's just run across what happened, like, internally, so what happened with the image? So I know we defined.
The data's still there.
Okay,
The data's still there, but it's, remember, this is like Rubik's cubes kind of thing, right? So it's like you took the Rubik's cube and you like stretched a part of it. So now it's actually 3-dimensional, but before it was 4-dimensional. And we just took where we had, imagine here we have the channels for each one, all the images, and then we had them as little squares. And now they're vectors. They're just 1 dimension.
okay, I see, so we put 32 by 32 in 1 dimension,
Yes.
that's how we did it. Okay.
Yeah, so we took the first row and then the second and the third and just stack them after each other.
Okay.
Yeah.
Awesome, thank you.
Yeah, it's, the data is still there, right? But we're just changing the dimensions. This I'm not gonna deny it. This is hard. This is what makes this difficult. Okay, so I'm not like saying it, you should totally be able to like do it, right? It takes a lot of practice and a lot of thinking about this. But this is one of, if you do this right, sometimes it saves you a lot of time in coding, right? To do it correctly. Got it? Let's try another one. We can do, how about we do that? Right, so if we do this, what do we get? Because it stretched it for all the 50,000, you see, so we're kind of, the -1 implies, or the 3 implies, keep this dimension as is, right, this relationship. But this, just make it 1. So all the data is still there, it's just really big. Now, one thing that is common about this is that there's 3 things in here now. What are they? The things related to red, the things related to blue, the things related to green. Do you see that? So technically that means for the 50,000 red grids, they're in one set or group, and they're 32 by 32, right, is also there. So we could potentially then take the mean of this and then have 3 values, which would be for all the pixels in all the 32 by 32 and all the 50,000 that correspond to red, we can average them out. Do you guys see that? And arrive, no? Yeah. Okay, so, yeah, go ahead. Yeah, please.
So, in the 50 or 5 million or 5 billion or whatever that is,
yeah,
it's gonna be the 1024 for each.
Yeah, there you go.
one,
That's a better,
50,000 times
yes, exactly. So what he said, right? So we had 3 by 32 by 32 by 50,000. Then imagine that you have 0, 1, and 2. Those are the three channels, red, blue, and green, right? And each one has 32 by 32 by 50,000. But then imagine that we make the 32 by 32 instead of a square into a vector of size 1024, and we still have 50,000 of them for red, 50,000 of them for blue, 50,000 of them for green. Then we do what Jason said. We're going to create a new vector and we stack them all after each other. So we take the first 1024, and then for the second 1024 goes after and after and after. And that's why we ended up with 3 of this size. Do you need me to do it on like the whiteboard? Make sense? Yeah. So that's kind of the idea. So yeah, that's a good one. They're in there. Okay. Now it just depends on how you want to do the if we're gonna average, let's imagine that we're gonna take one image, right? That is the car. And that has a grid, 3 grids, right? RGB of 32 by 32. And we want to take all the values in those cells and just average them, right? Or, calculate the mean or the standard deviation. So we might want to do an operation between each of those, right? And the average of all the grids, all the cells in the grids, all the pixels in the grids. So basically we could just take whatever this number is and take the mean of that and just get one value. And that's the mean. Then we can repeat the operation for the standard deviation, and then we can normalize. Do you see that? That's one way of doing it. And it should work, right? So that's kind of the idea. All right, so let's try this out. So I have this one, and now I'm going to take the mean of it and see what happens. So let's do view 1 mean, right? View 1 mean. And so now what we would need to do is grab view 1. Why view 1? Because it already has this shape. So in short, all I'm saying is we're going to take the average of all these 5,120,000 pixels, or whatever that is, 51 million maybe. Yeah. All right. So we can, to access that tensor, we do view 1. And now mean. Do you see that? Take the mean of it. And now let's just print that. So that gives you only one value. But what's the problem with that? It's mixing red, blue, and green. Maybe you don't want to mix red, green, and blue. Instead, you want to keep it as separate, a mean for each, right? So then how would you do that?
Just use the 0 as index.
Indexing, right? Indexing, because this is a tensor, right? So indexing it in some way. So here then, mean has a parameter called dim. Let's do 0. What do you think it did? For each, right? So it created basically, that's not exactly what we want, right? So instead, what if we do 1? Now it's for these, right? Okay. Does that make sense, guys? Before we meaned 3 of 5 million. And now we're gonna mean 5 million of 3, I guess. Yeah, 5 million of 3, whatever that number is. Okay, so let's run it. And the vector is now of size 3. Do you guys see that?
Yeah, I did mine a different way, but I got that same first number for red.
Okay, good.
That way it's a lot faster. You get all three of them at once.
Yep, I mean, yeah. I mean, good. If you, the way that you do it, if that's clear to you, that's perfect.
I like
This,
that better.
you like this, but yeah. So this, guys, is tough stuff, okay? And this is where you only get, this is why at the beginning of the semester, we started with all those NumPy and tensor operations, okay? Because just so that you're aware that if you develop your skills in this area, you become much more efficient in creating deep learning algorithms, okay? Any questions? Yeah, please. Yes, exactly. Exactly, that's the meaning of it. For each of the cells. Then that would have been only 3, but you would be meaning red, blue, and green. So you would have the average of red, blue, and green, which is not what you want. Do you know what I mean? Because there's red, blue, and green, and there's the vectors of 5 million, 5 million, 5 million. It's like if you can picture this, red, blue, green, 5 million, 5 million, 5 million. You took these 5 million, 5 million, and 5 million, averaged it, and got a 5 million one. But that's not what you want, right? What you wanted was red, blue, green, 5 million, make these 5 million into 1 for red. Then you have blue, 5 million, take these 5 million, make it into 1, the average of it. Then take red, blue, green, 5 million, take the 5 million, just 1. Got it? That's kind of what we're doing. And here I mean, at the end of the day, just show you how to play with these tensors, because we'll probably just use a function in the future to normalize all this data. But, you may want to do something like this at some point. Got it? Any questions? All right. So anyway, we did that. We can repeat this for the standard deviation. So that would be view one, and then, oh, sorry. Yes. Standard deviation. And that would be, oh, how did we do it? We did view one dot standard deviation and the same dimension, right? So the dimension would be 1, right? So now we want to print this as well. So I'm going to do print view one standard deviation. Okay, so let's go. Oh, and then, yeah, like that. And this one, yeah, there it is. Okay. And that just gives you the same idea, but instead of mean, we did the standard deviation. Got it? Okay, great. Yeah, so this will be a little bit more challenging when we do transformers. Transformers inside the algorithm have a lot of these operations. Okay, they create efficiency, so it'll take a while for us to write the code. I'll do my best to kind of try to explain it, but it's a complicated algorithm for sure. The most complicated in existence for deep learning, for sure. All right. Anyway, so we did that. We've played with this. Now let's get ready. So let's go back now to the code. Actually, it's 6:19. So let's stop here, take our 10-minute break. I'll pause the video. And then in the next video, when we come back, we'll just kind of go back to create our data sets, basically, and our data loaders. Okay. All right. So let's take a 10-minute break, and I'll pause